As Bill said, I'm going to talk about contribution by electrical engineers and scientists to the World War II Allied effort. So why did I do this? So I've been interested in World War II period for a long time. I had a father and uncle that served in the European theater of operations during the war. And as someone mentioned, I'm a docent at the Texas Military Forces Museum for the last 5 years. And the 36th Infantry Division, which is what the Texas National Guard became in World War II, was deeply involved in combat in Italy and in France and Austria during the war. So because of that, I thought that's a lot of my interest in this topic. So as I said, I wanted to dig deeper into it. And so one of the things I came across, and I'm sure you've heard of it, is that mythical, hey, if you study something for 10,000 hours, you're an expert. So I started tracking that on myself a few years ago, and I'm nowhere close to 10,000 hours. I've got up to 2,500 in 5 years. You know, it's like, I'm not sure I'll ever hit 10,000, but I've been certainly working on it for a long time. Why we're doing this tonight, this year, IEEE History Committee designated the first week of October as IEEE History Week. And so while this isn't during that week, we're during as close as we have for this organization to have meetings at that time frame. So I thought this was a good topic to share with people at tonight's meeting. And as I said in my teaser, if you will, there were a lot of contributions from Colossus to Loran, from the proximity to fuse to G, and a whole bunch of others. And the more I looked at it, the more that whole bunch of others grew. So I will not be going through detail in all 100 plus slides I have, because we'd be here for hours, but I'm going to hit the high points as best as I can. So that's a quick overview of what the topics are. You probably can't read it in detail. I tried to organize them into groups, but that was kind of hard in some cases, but that's the order that I'm going to follow. And I'm going to probably go pretty fast because I've got a lot to cover. Now, the first thing I want to talk about is preparation. And I mean preparation for the war by the U.S. Two things happened. First of all, FDR created the Scientific Research and Development Office. It was an organization formed in 1940 to start promoting technological development in preparation for entering the war. And it involved a lot of funding. It's basically what became later the National Science Foundation. But there was this, and then it evolved into another organization, the Office of Scientific Research and Development. But those funded a lot of research, both in the public sector and within the military, prior to and during the war. The other what?
The other side file. No, it's this computer.
Okay. Well, it could be this one, but honestly, I'm not sure how to turn it off. So the other thing that happened prior to the war is the British, fearing invasion by the Germans and wanting to preserve their technological achievements, visited the U.S. in 1940 also. It was the Tizard mission. And what they did is they came here with many technological achievements. They shared their work on radar, on jet propulsion, and on their work on atomic weapons. So this was setting the groundwork for a lot of joint venture over the coming years. So one other thing I wanted to mention, because it's going to come up as I go through this, is IEEE has something known as the milestone in electrical engineering and computing. And I won't bother reading all this, but it's done by the IEEE History Committee. It can be proposed, a new milestone can be proposed by any section in the world, but it has to be something of significance, and it has to have occurred at least 25 years in the past. So that gives plenty of time for people to determine that something was a major contribution to the field. The reason I bring this up, as I say, as I go through here, there are several things I'll talk about which have had milestone designations. And you can go to a list at the IEEE history site, and it'll show all of them. We have a few here in Texas, although I don't think there are any in Austin. So that brings us to the first field, and the field that I'm most interested in, which is computing. That's where I spent all of my career. I just put the second tab in here is up until the 40s, when machines started to be developed, computers generally referred to a room full of women with calculators doing calculations. That's how most of those big computational tasks were carried out. Computers, as we now know them, started to enter into this and replace those big rooms full of women. I'll just mention a couple of things. The Model 1 is a digital calculator. It was built by a fellow at AT&T, although it wasn't AT&T then, but Bell Labs. But it was all done with relays that he basically telephone relays because he had access to them. And he built a couple of these machines for the military. They were cost at about $20,000. And these were massive machines, seven number memory. It could add, subtract, multiply, divide complex numbers. But it took 440 relays to accomplish this. So we're not talking about a calculator, in your hand. We're talking about a massive machine. And it was used by the military for some special purpose things. Not quite a computer, but I thought it was interesting from the aspect of it was a beginning. And actually, this gentleman is the one that was credited with, as I talk here about building the Model K. He went home and with a few of his relays and some wire and cut up some tin and basically built a 1-bit adder. And then took it back to the office and said, "Hey, look what I've done. I've got a digital adder here." And that really started him on the development of the later machines, and he went on to do other things. And somewhere in here, I have to mention that he's the one that came up with the idea or the concept or the terminology of digital. And he introduced that terminology. So even though these machines were massive, built out of a lot of relays, they were reliable, something that some of the other machines weren't necessarily accomplishing. Quickly move on. The next step in that is the U.S. Navy bombs, spelled BOMBES. Now, these were machines that were built on the design that the British had created. These bombs were used to help decode the messages that they were capturing in Bletchley Park. And they had several of these electrical mechanical devices, but the U.S., because of our ability to manufacture far more than the British, we started building them here. They were run by the Navy, built by National Cash Register Company. The design was, pardon me. I start to talk and then I run dry. So these were started to be developed in January 1943. They were electromechanical devices and were pretty massive themselves. The first two experimental devices went into operation in May of 1943. They were running in Dayton, which is where the development was, but once they went into production, they were moved into Washington, D.C. Okay. I've read over this so many times, it all runs together. Once these were proven, the Navy got funding for a full $2 million. And I thought this was great considering the kind of time frames we have today. They put in their request on September 3rd, 1942. They got the $2 million approved the next day. Something our Congress would never happen now. So the laboratory constructed 121 bombs during the war, and they were used by code breaking for the U.S. Navy, signals intelligence unit in Washington. The war, they finally stopped production in 1944 because by that time they really didn't need more of them. The war, they could see the end of the war was in sight, and they could more than handle the German message traffic at the time. As I said before, these were massive. They were 7 feet high, 2 feet wide, 10 feet long, and weighed 5,000 pounds each. These were big machines, and they had 121 of these running in the Navy Department. So this was a significant milestone, and it was recognized by IEEE as a milestone. And it's actually outside the building in Dayton, Ohio, designating it as a location where all of these bombs were developed during the war. Pardon me. Moving ahead, the next step in this, we really get to something that is more electronic than electromechanical, and that was Colossus. Now, Colossus was a machine built at Bletchley Park. Certainly Alan Turing and others were very instrumental in the design and the creation of the machine. It had an electronic memory, and it was programmable. Now, programmable was pretty liberal there in the terms because it wasn't writing a program, but rather you had a big patch panel and you had to repatch the wires to rewire the machine to do what you wanted it to do. It's hard for me to adjust it. I just have to sit back. I am told my head was cut off. So, but the slides are what's important, not me. So I have a picture here. I've tried to capture photos that depict these devices as best I can. Some things that just can't find photos of, and others, well, I've got them where I can. So this was a picture of the machine. A lot of Navy or British. Oh, what was the right designation? Do I have it in here? The Navy women in the Navy in the UK, and I can't think of what they were called, but they ran a lot of these machines at Bletchley Park. The prototype, there were several Colossus machines built during the war. The Mark I entered service in December 1943 and was put into service at Bletchley Park early in 1944. An improved Colossus Mark II using shift registers to improve the processing power was developed soon afterwards, and 10 of those were in use by the end of the war, with an 11th in production, but it was never put into service. The Mark I contained 1,600 valves, British called for vacuum tubes, but 1,600 vacuum tubes. The Mark II had 2,400 vacuum tubes and became operational just before D-Day on June 1st, 1944, and was thus employed for code breaking from that point on in the war. I'm going quickly. If you have a question, let me know. Next up on the list is the Harvard Mark I. Now, the Harvard Mark I was a joint project between Harvard University and IBM. They built this machine had a fancy name, automatic sequence controlled calculator, but it was just called the Mark I generally. It was a 70-ton electromechanical device. It was installed on the campus of Harvard University in 1944, and it was really considered to be the first computer which could be programmed to execute complex operations. It looks pretty modern in the picture.
I think it's still there.
I think it is in the computer museum somewhere. In fact, that photo may be from the computer museum, cleaned up vastly from the basement where it was actually built. So Grace Hopper, which everyone is aware of, she was a lieutenant at the time when she started. She was one of the early programmers of the Mark I at Harvard. The Mark I consisted of a steel frame 51 feet long, 8 feet high, and it held the calculating unit. It had interlocking panels of small gears, counters, switches. This is a mechanical engineer's dream. This is where you kind of start thinking steampunk is real, because it was a lot of combination of electrical, electronic, and mechanical computation. But it had 500 miles of wire with 3 million connections. I think an engineer that does reliability design would have a headache with this one because of so many physical connections. 3,500 multiple relays, 35,000 contacts. I won't read the rest, but it was significant in what it contained. But it was significant too in what it could do and how it moved the computing field forward.
You call these analog computers?
No, these are all digital computers. It's not analog. The military had a lot of analog computers as well, and there were several attempts to go, and somewhere in here, I think with Whirlwind, I talk about they were trying to design a simulator. They initially were going to build an analog computer. But the guy in charge went to a conference and heard about, can't remember if it was this one or ENIAC, but he heard about digital computers, throwing out the analog computer design. If we can build it more reliably, thank you, with a digital design. So again, there is a IEEE milestone at Harvard University recognizing the fact that this computer, the significant movement forward in computing, was designed, built, and put in operation there. Thank you, Kai. And get more water out of here. This one's got a little tiny hole. So moving forward, and now I get into 3 computers, and I put them here, but I've also designated them as honorable mentions. And I say this because they were conceived, often designed, and even construction begun during the war, but because the war ended when it did, they did not actually go into production for the military effort. But this one is ENIAC, and it was a machine developed by or requested by the Army to do artillery ballistics tables. Now, why is this important? Well, I thought this was interesting background. So it took about 20 hours for a human, one of those computers I talked about earlier, to calculate one trajectory for each new gun. Now, in each new gun, and we're talking about artillery pieces, anti-aircraft pieces, anything that's shooting a projectile, each gun would in turn need as many as 500 trajectories calculated. So the artilleryman would have a table, a book that would say, if I want to hit this location, then these are the sittings and angles that I would need to put in so I would hit the target. So they needed to have these. Yet with 500 trajectories needed, it would take about a month for a human to make that calculation and produce that table. And the military was coming up with one new artillery piece after the other. The Army saw the need to automate this, and so they contracted for ENIAC to be designed. It was built at the Moore School of Electrical Engineering, and under an Army contract for collecting ballistics. Work began on the machine in 1943, but didn't finish until 1946. So it missed the end of World War II. But it was the first programmable general purpose digital computer. And again, we're looking at a room full of equipment. I thought I put it in here, but maybe I didn't. Let me jump ahead to the next one. Yeah, I think I put it here. So it used pluggable boards for communicating instructions to the machine. Again, this was something that required days to hand program and to put the plugs to connect the various pieces of the machine together to do the job you wanted to do. ENIAC was built in a 50 by 30 foot basement at the Moore School. It consisted of 50 panels arranged in a U shape around 3 walls. And you can kind of see that in this photo. The photo was taken from the free wall, and everything is wrapped around the outer sides of the room. So each panel was 2 feet wide, 2 feet deep, and 8 feet high, with more than 17,000 vacuum tubes, 70,000 resistors, 10,000 capacitors, 6,000 switches, and 1,500 relays. It was the most complex electronic system built up to that time. When it was in operation, it generated 174 kilowatts of heat. It was a room heater by far. It cost $400,000 to construct at that time, and had a high-speed memory based on vacuum tube circuits that could execute up to 5,000 additions per second. So a significant improvement over what we've talked about before. It again achieved an IEEE milestone. So outside the Moore School, there is at the University of Pennsylvania is a designation that says here is where the machine, the ENIAC, was built in completed in 1946. We're almost run out of the milestones because we start running out of physical things. So EDVAC is another honorable mention. I'm not going to go into too much detail here, but again, they realized that they needed a general purpose machine. In 1944, they started designing it. They wanted to come up with this general purpose machine with an electronic memory. It used a mercury relay lines as its memory, so it could store so many numbers in those lines, and then had a high speed, and I'm sure the way that was described, a serial memory, because the data would have to circulate down the mercury delay line and then added back at the top end to go through again. So they could store over 1,000 40-bit binary numbers. And because of that use in memory, EDVAC did not use as many vacuum tubes as some of the earlier machines. And it went into operation in 1950. Again, and the last honorable mention is Whirlwind. In the Navy, they wanted to produce a simulator, a more accurate simulator. And the idea, to follow your question earlier about analog, thank you. Analog machines, that was his first solution. He wanted to take a link trainer and instrument it and be able to give pilots a more thorough understanding of the aircraft and test those aircraft as best as could be done in the lab before they took it out and started flying them. So that was his intention, to replace at least part of the wind tunnel training and the actual flight training. So he came up, he had the idea during the war. As I mentioned earlier, he went to a conference in 45, but by October, the war was over. But he decided at that time, analog wasn't going to work. He needed to go digital. And so they ended up building the digital flight simulator. It cost $1.2 million and did not get completed until June of 1948, but went into, it was cost $1.2 million, delivered in June of 48, but it didn't go into operation until March of 51. It had an electrostatic memory, and it ran about 35 hours a week. So we're not talking about a high production machine. Still large, occupied 2,500 square feet and used 5,000 vacuum tubes, as well as 11,000 crystal rectifiers. And as with the others that I've mentioned, it too received recognition from IEEE with a milestone award. So many of these are back east. You could go have a road trip and visit all the milestones. Now we get into some other things. I don't even know where my time is. Okay, let me know if I start running short, because then I'll start skipping some things. As I said, I'm on slide 31 and I have 100. So we'll have to skip some things, and I'm going to have to quit talking and reading so much. G is a system that was developed by the British. It was originally conceived as a landing aid to be able to bring in bombers when the weather was inclement, just bring them in. And what the idea was is they would have two transmitters at right angles to another. And then the aircraft, as it came in, they could look at an oscilloscope, look at the signals, and by measuring the time difference from the signals, I'm paraphrasing all this, from the signals, they could tell where they were and get close to the airbase. Soon after, they decided, well, this works for bringing aircraft into landing. Could we use it on a bigger scale in our night bombing efforts over Europe? And so they built out a much larger system, many more antennas, and have with much greater degree of separation of the antennas. And what they were able to do is to use this to get within a few hundred feet of a designated location over a city in Europe, up to 350, sometimes farther away. So because they were doing night bombing, they were using these in the Pathfinder aircraft to go in, find the target. They would either illuminate the target with flares, or they would use incendiaries to mark the target. Then all the other aircraft would bomb on the location that was marked. And this was a big improvement over their accuracy. One of the things, and if you read much about World War II history, is everyone that flew bombers and were in charge of the bombers says, man, we can hit a dime from 50,000 feet. Certainly that was almost the claim of the Norden bomb site for the US. Reality was, if they got within a few miles of the target, they were doing good. There were some analysis that went on. I can't remember if I included in here, but they went on, did an analysis of some bomb raids, and they go, the closest bomb was 5 miles away. Some of them were 50 miles away. Yet the pilots and the bombardier says, we were right on target. So it was a big problem. But G was able to guide them much more accurately when they went into bomb. It went into operation in early 40s. The first few units were all handmade rather than coming off the production line. and they were delivered in early January of 42. In all, 660,000 G units were produced and used by all the air forces that were bombing in Europe. This was a device used for the European theater. First operation took place in March of 42 with 400 aircraft. They were attacking Essen. They had a G unit installed on one of the Wellington bombers that was leading the raid. And they thought this was a success because that 33 of the aircraft actually reached the target. So, we're talking about incremental improvements here, but it did help a lot. Then they did later in 42, they attacked Cologne. And again, the crew at least said that the G unit allowed them to mark the target with incendiaries and bomb it more accurately. As I said, they would use two transmitters, and someone would watch an oscilloscope and measure the distance between pulses to measure the distance and know, am I on target? When they got to a certain point, I'm on target, I can release the bombs. And if we go back to there, you can see on the right the oscilloscope. And so this was used by, and I think I say in here, not too far. The navigator or radioman would typically use this rather than the bombardier, because he would be steering the aircraft towards the location. So this was a big step forward, innovative, but kind of kludgy because you had to read it manually. And as with many things electronic, as the Allies were developing new systems, the Germans were figuring out how to jam them and to have developed countermeasures. So a lot of this stuff worked great in the beginning, but then deteriorated as the war went on, as the Germans figured out how to countermeasure it. And so distances became less and accuracy became less. Now this evolved into the Loran system. Now the Loran system was built here in the United States. It too was a hyperbolic radio navigation system, measuring time delay between two different signals. Now the British G system used a higher frequency. For Loran, they chose to use a lower frequency because they wanted longer range and accuracy wasn't as important to them. They wanted ships at sea crossing the Atlantic or in convoys going down the coast to know about where they were. They didn't have to know within hundreds of yards. A few miles would do in terms of that. So they developed that system. It was ordered in 1940 and went into operation in 1943. It was used by both vessels as well as aircraft. And the whole concept was similar to the G system, except running at lower frequencies. But it had a range of up to 1,500 miles, whereas G only went up to 300 or 400 miles. And its accuracy was in ranges of 10 miles. But it served the purpose, and it was used for a long time. Okay, I talked about that. It also saw a lot of use in the Pacific, because in the Pacific, distances are so vast, finding your location if you're out of sight of land was very difficult. So they were able to use Loran, deploy it throughout the Pacific theater. And because of this, aircraft, for instance, could load with less fuel because they knew that they could more reasonably and timely find where they were headed. And then they could trade off that fuel that they didn't have for additional bomb load if they were going on a bomb mission. Okay. So by the end of the war, there were 72 Loran stations in operation and over 75,000 receivers in use on ships and in aircraft. Again, this is something that received a milestone. And again, it's back east at Cambridge, recognizing the contribution of Loran to electrical engineering. And certainly this followed on after the war, used by commercial vessels to navigate and find their way in commercial aircraft. Moving on to anti-submarine warfare. I'm going to start going faster here because we're getting close to 9. Well, we have time. We have more time than I think. Okay, so the British anti-submarine warfare was important both in World War I and World War II. The British started developing a sound-based system right at the end of World War II called ASDIC. It was used by the British in the war. The technology was transferred to the U.S. on the Tizard mission that we talked about earlier. So the U.S. got that, as well as research that they had been working on in sonar in the Navy Department since the 1930s. So there were a lot of developments in underwater recognition and location determination of submarines. One of the problem with ASDIC was the nature of it was if a destroyer was going to drop depth charges on the submarine, it lost the submarine as it got over the top of it. So the submarine could easily take a different path and they might lose it. So they ended up altering their strategy and did a creeping attack with 2 vessels. One would be the active vessel looking for the submarine. They would guide a second destroyer over the submarine, which would drop its depth charges. And then the vessel that had been sounding the submarine would rapidly go and drop its depth charges in the same location. So they were able to be more effective. So that's enough of that. Sonar, which was essentially the US's version of ASDIC. As I said, they began work on it in the Navy Department in the 30s. By the 40s, the sensor was a magnestrictive transducer in an array of nickel tubes connected to a 1 foot diameter steel plate attached to a shell salt crystal in a spherical housing mounted underneath the vessel, underneath the searching vessel. It could also be mounted on a submarine to search for other submarines or things. They replaced those shell salt transducers with ADP crystals later on, and that proved to be more effective. And they produced thousands of these during the war to put on ships to hunt for submarines. Okay. They did. Everyone's seen in movies, you ping something, you hear a sound bouncing back. That's what they were doing to try to find the submarines. They could scan 180 degrees arc out to about 5,000 yards in a 5-degree increment. So they could scan the waters looking for something and listening for a reflection. And it took about 4 minutes to do a complete search. Part of the problem is that sound travels at a slower rate underwater. So that was deployed extensively. That evolved into FM sonar. That was a patent filed by the Navy Department, which used frequency modulated pulse active sonar, and it was shortened to FM sonar. And this allowed the tracking of multiple targets at one time. So it was a big step forward, and was developed in 1943. Another development was the proximity fuse for depth charges. And I'll talk about a different kind of proximity fuses later on. Again, this was a patent filed by the Navy Department. They put in a fuse in the depth charges so that it would sense the magnetic field of a ship, of a submarine. and only when it sensed the being near the submarine would it go off. So that way, a anti-submarine vessel could tell if they were near the submarine, because if it went off and they would see the results on the surface, they knew it that depth charge had to be close to the vessel. And so it was used to it improved the attacks on submarines during the war. Another device was the FIDO, and you see this sometimes called a mine, but it was also, I think I read somewhere where they designated it as a mine to obfuscate to anyone looking at the name that it was a torpedo, and it was a acoustic torpedo. Development began in 1941 and went into service in 1943, and it was used well after the war. Approximately 4,000 were produced, 3,000 were actually used in combat or deployed in combat. And of the 204 that were fired, they ended up sinking 37 vessels and damaging 18 German submarines. So it was pretty effective against other submarines, and that's what it was. The goal was. It was kind of an oddball thing. I thought I had a picture of it. There it is. The next slide. So it was 19 inches in diameter, 84 inches long, and weighed 680 pounds. Not a lightweight device. And it had almost 100 pounds of explosive in the nose. And you can see a drawing of here. I thought it was unusual that, looking at it when they designed it, they used an off-the-shelf washing machine motor from General Electric to drive the thing. It's all electric, had a single propeller, had a 48-volt battery, lead acid battery in it. That's contributed significantly to the weight. It could reach speeds up to 12 knots and run for 10 minutes. So that gave it a range of about 4,000 yards. So if you could find the enemy submarine and using sonar determine where it was away from you, you could then fire this torpedo in that direction, and it could acoustically seek out that submarine and home in on it, hopefully making a hit. It had an onboard homing system of hydrophones and a vacuum tube signal processing system for proportional steering. So we're getting into real electronics, so we're still into vacuum tubes. Passive sonar arrays, these were developed, I'll mention it only mostly for a moment. They use the same ADP crystals, but they would chain them together in long arrays so that they could be drugged behind a ship or sometimes behind submarines, giving them more accuracy. Another device used in anti-submarine warfare is the bathythermograph. There's a lot of stuff in here I had a hard time pronouncing. Basically, what this device does was to measure the temperature layers within the water. If you were in a ship, a destroyer or a frigate that was chasing a submarine, you needed to know what the temperatures were in the water, because they created strata that would allow the submarine to hide beneath a certain layer of water, of temperature water. So they would take this, they would drop it off the back of the ship. It would rapidly descend to up to 900 feet, pull it back up, and then they could look at a glass plate in there, and it would record the temperatures as it went down. They could then use this to refine their hunting of the submarines and know whether there was perhaps some kind of a layer that was obfuscating the submarine from the sonar. They were also used, okay, I already said that, but they also could be used on submarines. They put a bubble like the sonar unit above the submarine's hull on the outside, and just have instrumentation that the submarine could get looking at water temperatures, so they could go, we just passed through a layer. Here's a place that I can hide. And again, you see that often referred to in a lot of modern thriller movies that have to do with submarines. So it was an aid to them. And again, it was an electronic device. A little bit about electronic warfare. I didn't go into a lot of depth here, but both sides during the war had jamming equipment. Both sides were using radio guided munitions and radar. So countermeasures were developed to interfere with all of that by the other side. Lots of different systems were developed and used. Drones and guided bombs. So one of the first guided bombs was known as the Azon, and it was a 1,000-pound guided munition. It was dropped like a regular bomb, so it had a ballistic trajectory in terms of altitude. It was going to follow that path regardless. But what it had in addition was a steering system, the Azon unit, that allowed it to adjust its azimuth, steer left and right to more accurately hit a target. And it was used in both the European theater and the CBI, the China, Burma, India theater during the war. A similar device was the US Navy BAT. It's shown here between a TBF Avenger carrying it underneath. It was a more advanced guided missile. It was truly a guided missile, and it was used in combat. It had a long range and was considered to be very accurate. It had its own onboard autonomous active radar seeker, so it could find its target. It was used primarily in the Pacific theater starting in 1944 and beyond. Sometimes it had a hard time determining a target from clutter, but they made some refinements to it. These again weighed 1,000 pounds, and as I said, uses active radar to home in on the target. Drones were developed too, and this was an interesting program, and I went on a little farther than I it was interesting, so I went on farther. Dennis actually mentioned this to me. There was a project that was developed in called Aphrodite. It was to use obsolete B-17s and PBY-4s as essentially radio-controlled bombs. The U.S. Air Force Commander Hap Arnold directed the 8th Air Force to begin a research project and develop this. Okay, so these bombers that was going to be used as guided weapons were stripped of everything. The only thing was the instrument panel left for the pilots, and the pilot and the engineer seat. Everything else was stripped. If it could be removed, it was removed, because for every pound they took off, they could put another pound of explosives in the aircraft. So they were able to strip almost 12,000 pounds out of these aircraft and increase the payload by that corresponding amount. They were lacking a control system, so they ended up adapting the Azon system that I talked about earlier. But remember, the Azon system only allowed you to steer in one direction. So their solution was to put 2 of them in there, one that would steer horizontally and one that would steer vertically. They also were using television, and I'm actually going to talk a little bit about this later, but they were using this in weapon systems well before the public saw much use of it. And they had cameras inside looking at the instrument panel in the cockpit, as well as one looking ahead out the forward windshield, so they could use it to guide the aircraft into their target. The transmission was sent back to a what's the right word for it? A mothership that was following behind them, a few miles behind them, so that you had the pilots that would fly the drone aircraft there, and they would fly it into their designated target and hopefully blow up what they were trying to hit. Antenna in the tail of the drone B-17 transmitted the signals, and an antenna in the nose of the mothership received the signals. These were flown by a volunteer crew. I mean, you're flying on a lot of explosives. They take it off. The idea was the pilot would take it off, get it up to 2,000 feet or so. You would pass control to the mothership, and then the pilot and the engineer would bail out. I mean, kind of a risky thing, but you know, when you're able to deliver probably 24,000 pounds of payload somewhere, it might be worth it. They were able to update the navigation system from the Azon to an improved system called Castor. I didn't see much detailed about it. These were used mostly in targets that were not protected heavily by flak because it would have been an easy target to be able to hit. The project ran until almost the end of the war before it was canceled. One thing that was notable here is they flew 14 missions with this system. Most of them didn't work. They failed to hit their target. They were shot down. They crashed. They wasn't successful. But the one notable thing was Joseph Kennedy, the older brother of John F. Kennedy, was one of the pilots that volunteered to fly these. And his ship blew up before he and his engineer were able to bail out. So that's sort of a notable detail for that program. That gets us to radar. When do you want me to wrap up, Kai?
Well, still half an hour.
Half an hour, okay. I am sure I can fill that time. So radar, a lot of things here. People, when I was doing all this research, I kept coming across someone that says, this development was this is what wanted for the Allies. It was it. And that's for 4 or 5 different things. So they all had their contributions. But here's historians have claimed that radar helped the Allies win the war more than any other technology. And this probably has some credibility to that statement. One of the first radars that were on the Allied side that was deployed was the chain home radar system in the UK. Now, it was completed early. The British was already thinking about attacks from the Germans. So they built up this system along the south and the east coast of the UK. These were very tall towers that allowed them to detect a flight of incoming German aircraft up to 30 minutes before they arrived over Britain. So they could then, using the doubting system, RAF guy, would be able to scramble fighters and have them already in the air ready to intercept the incoming bombers rather than wait until they came over and were seen by coast watchers and alerted. So they had a much better chance of shooting down, or at least shooting down as many as they could of the attacking bombers. It was a sophisticated network. They could detect aircraft up to 80 miles. It worked at 25 megahertz. These towers were 100 meters high, so they were not small. Amazingly, I'll get to it in a second. They used a pulse radar system. They just kind of broadcast in the general area, and they were looking for fleets of large number of aircraft coming in. Onesie, twosies, not so much. So we're looking for big groups of aircraft. And they could, by adjusting a dial on their instrument, the operators, and most of the operators were women. RAF men were sent out and stationed there to do the maintenance, but the women were the ones that were watching it to look for the enemy aircraft. One interesting thing with this is they're massive. I mean, they're right there on the coast. The Germans, every time they flew in daylight, flew right over them. Yet they only attacked them once during the war. And part of that was Hermann Goering, the Luftwaffe commander, was convinced that they were just a bluff. So he just said that they're not important. And yet they were a massive deterrent to the oncoming bombers from the Germans. One of the most significant things that was developed was the cavity magnetron. Now, the cavity magnetron was developed by the British. It too was brought over to the U.S. with the Tizard group and shown to the U.S. A lot of development was done with it at MIT in the radiation lab. So it is a significant contribution. The big thing is it allowed the generation of microwaves in a very small space. The home chain system had massive facilities. So it wasn't something you could put in an aircraft or in a ship very easily. The magnetron, on the other hand, or the cavity magnetron, was something that could be built on a small enough scale to go onto aircraft. And I'm not going to read all the details about it, but it was unique in that it used a combination of electrical flow with a magnetic field to generate high power microwaves. I said that. So these were capable, they were pulse unit, they were capable of putting out 500 pulses per second. So nearly continuous signal, but they were able to send them out 3,000 megahertz and about 450 kilowatts in terms of peak output. The government contracted Raytheon to build a lot of these during the war, as well as the radar systems. It too was recognized with a IEEE milestone at in the UK, because that's where it was truly developed. But it was refined here in the US, and they were built in high quantity during the war. You know, I saw this and go, was the radar system in Hawaii really that significant? Well, kinda. The Army, by the time 1941 rolled around, had already started developing and deploying radar units, and they had some deployed in Hawaii, on Oahu, the SCR-270 system. And you can see a photo here of it. It's not small, but it's portable. It can be moved around. 5 of these units were deployed in Oahu. Yeah, I'm saying it right. Oahu, and the crew were being trained on it. And the morning of December 7th, 1941, all but one of the crew had already stopped their training, shut down everything. But this one fella noticed all these blips all of a sudden on his radar. And at first he thought the radar was at fault. But finally he decided, well, there's something here. And so he called higher levels of command, and you're a trainee, you don't know what you're doing. So they saw the incoming Japanese, but because of lack of confidence in the equipment and their training and officers in their new crew, no one took any real notice of it. They couldn't, without the other stations, they couldn't triangulate. So all he knew is there was a bunch of stuff out there somewhere, and he couldn't figure out how far away it was because the other stations had shut down. This too has been recognized with an IEEE milestone, and it is in Hawaii. The Hawaii section put it through, and it recognizes the fact that the Japanese attack was detected by radar, and the naval base could have been warned if they were prepared to accept that information. Proximity fuses. Now, I thought this was a unique aspect of radar. I mean, we think of artillery fuses as something that's small, and most of them were. They were primarily timed or on impact detonation. But if you're trying to shoot down an enemy aircraft, you got to get really lucky to hit it. And then if you're trying to use a timing or an altitude setting, you're trying to guess, well, how high up are they? And are they moving up and down? where do I want to sit this? And you're shooting and you don't know how accurate they are. The proximity fuse uses Doppler radar inside the artillery shell to notice the approach to an aircraft. It can sense when it's coming close, and it suddenly goes, oh, I'm starting to move away, explode. So you're close enough so that the cloud of shrapnel would be at least close to the aircraft. So that was their goal. So these were fitted in a large number of artillery shells, even mortar shells eventually. Part of the application too was not just against aircraft, but they used them in artillery shells to say, I don't want this artillery shell to fly until it hits the ground to explode, or fly until it hits a timer to explode. I want to know how high I am above the ground. So they actually could have a sitting. They go, I can make this explode at 7, 13, or 33 feet above ground level. So these could be used in for to great effect when you had a large number of troops or vehicles in an area and you wanted to destroy them. Again, it's another one of these things. Like, this is an important development of World War II. And it was a guarded secret until well after the war. General or Admiral Struce, I'm not going to read it, but he attributed the BT fuse to be a significant contributor to the defense of London and to the Navy in the Pacific. Fuses like this had a rigorous requirement. I mean, you're firing this projectile out of a cannon. So you're having 20,000 G's of acceleration. Rifling in the barrel is spinning it. So it's running at close to 30,000 RPM. So it's generating huge centrifugal forces. So it wasn't simple to develop this. I thought it was interesting that their solution to developing this was using miniature hearing aid tubes to just withstand these really rigorous conditions. So they could build they could build these proximity fuses with 4 or 5 vacuum tubes. One was an oscillator. They had a transmitter and a receiver, and they were used to detect, had a filter to look at things. It was a low frequency signal. They were looking for something close. When the reflected signal got high enough, another tube fired and it exploded the round close to the target. A lot of the electronics industry by 44 was making proximity fuses. At the start of this in 1942, a proximity fuse cost over $700 to produce. By 1945, the cost had dropped to $18. So the military purchased over 22 million of these fuses and used them in both theaters of the war. They were 20 times more accurate than the other fuses that they replaced. Yeah, so some 8.3 million were produced during the war. They were a significant contributor to taking down the V1s because the British had a whole chain of anti-aircraft guns along the coast, as well as around cities. But as the V1s would come over, they would attempt to shoot them down. Once they started using these proximity fuses, they increased their hit rate by a significant margin. It rose from 17% to 74%. So it was a big contributor to reducing the number of V1s that actually went into England. 200,000 of these fuses were used in the Battle of the Bulge to hit ground targets. Patton credited their introduction to saving Liège, and their use in his mind required a whole revision of land warfare because it changed how artillery was being used. Okay, got a few more minutes. Fire control radar, and I'm not going to go into detail. They actually had fire control radar primarily for anti-aircraft guns during the war. They would have a big trailer with a big parabolic antenna set up, and they could then direct the artillery pieces that were going against anti-aircraft to try to be more accurate in terms of hitting them. Used first in the combat in 1944 at Anzio in Italy. Very timely. I'm not going to bother reading that. So trying to finish in the next 17 minutes. The British developed something called the H2S system. This was used, they wanted to be able to look down at cities, being able to identify targets more accurately. They had G that put us in the general area, but they couldn't accurately at night actually see what they were dropping bombs on. So using the magnetron, they were able to put the H2 system in the aircraft, and it had a high frequency so we could scan the ground, so we could see the city and the structures in the city and use that to find their target and drop their bombs more accurately. Yeah. First went into use in summer of 43. They found it to be very useful. I mean, they could really see buildings in their radar screen. So this really improved the accuracy of the machine, and there were some evolutions of it. And that's something I've said, of all this stuff I've talked about, there was one evolution of it after another of it. So it's not just one G, there was like Mark 1, Mark 2, Mark 3, and so forth. And the same with many of these other things I've talked about. And it was widely deployed. They put them in everything, in all their night bombers, to be able to more accurately hit their targets. And from that, they evolved what was called fish pond, or the British Type 182 radar. The basic took the same thing, tweaked it a little bit, and go, instead of looking at the ground, I want to look around me. So they were using it to detect night fighters and be able to avoid them or start firing on them more easily. A long thing to go here. I'm going to speed up. Gibson Girl emergency radio. We stole the design from the Germans. We reversed engineer it, and it was used extensively by aircraft crew all over in both theaters during the war. It was a simple hand crank device. It had a fixed frequency setting. It had a fixed distress call. It came in a sack with an antenna, a kite, and a helium cartridge and a balloon. So if you were stranded out in the middle of the Pacific somewhere, you could send it up and start cranking away and sending a signal. And they were called Gibson Girls because of the shape, the kind of hourglass shape. And they were made that way so you could sit it between your thighs and hold it while you were cranking on it to send the signal. But they were made in vast quantities and used by I think the U.S. and as well as the British. Okay, I'm not going to go any further. I kind of went down into too much detail on some things. So that they used it a lot. Again, it was a reverse engineered design, but it proved to be very effective, and it was in use well after the war on aircraft flying over water. VHF radios, line of sight radios were used a lot because of the nature of trying to pick up down pilots. You had line of sight. If I recall, the Gibson Girl went 2,000 feet or 2,000. That 2,000 feet sounds wrong. Had a range. It quoted as could talk to an aircraft at 200 miles away, flying at 2,000 feet. So if it was looking for you, and relatively close line of sight, it could find you. And the VHF radios were also used in the same fashion. Walkie-talkies we see everywhere in movies, and there's really two different kinds here. A lot of controversy as to who first developed it. There's about 5 different groups that claim that they did. But they all developed something and it all went into production or was contributed to production. One guy or outfit in Canada built a unit. It went 18,000 of those were built and went into deployment. Motorola, however, was the one that was attributed to really building and deploying most of them. There was the little SCR 536 handy talkie, or what you really think of these as walkie talkies. 40,000 of them were built, and they were in use everywhere in the military. They also built the SCR 300. 50,000 of these were built, and it was a backpack style radio, and it was again used all over in all theaters of operation. Communications became a big, significant factor in the war. Sigsally, and I'm going to paraphrase this, it was developed in 1943, and it was essentially an encrypted telephonic system that allowed you to have multiplex signals and encrypting the data. And they would deploy these systems throughout the US, Europe, and the Pacific, allowing telephonic communications between the Pentagon and theaters of operation. And it was encrypted in such a way that even if you picked up the signal, at least they say at the time, if your enemy picked up the signal, they would never be able to decode it. And the IEEE recognized it as being first in 8 different areas. I think I put them here. Yeah, all of those. Everybody can look at these slides later where we don't have as much time, or not short time. But they were used primarily between headquarters units in DC, London, Paris, North Africa, Hawaii, Guam, Manila, Australia, and other places. So this would allow telephone communications, very rapid transmission of data from the Pentagon to commanders in the field, and it would be encrypted and safe from listening. I had never heard of Sigsally until I was doing this. Radio relay was something else that I came across that was interesting. And radio relay in this context is doing relaying of teletype signals. So what they were able to do is to have teletypes in the US talk directly to a teletype in England or to commanders in the field. And it would route the signal over radio channels so that you could send over this wide network and get information directly to the field commanders. Television was used in training back then. Again, I didn't even know they were using television, but apparently they were doing it to have one trainer talk to a multitude of classrooms. Didn't get a whole lot about it other than they did use it. I'm almost to the end. I got down to miscellaneous stuff. And I was like, I didn't know where to put this. So there were magnetic mines. Before we talked about being able to, well, we haven't talked about that yet, but being able to develop a magnetic mine, drop it in the water, and instead of it waiting to a ship contacting it, it would sense the ship going over it or near it to explode, much like the magnetic fuse in the torpedo we talked about earlier. If that mine went off under a ship, it'd break the back of the ship. So they were very effective against shipping. Not, you know, they had this either. Infrared night vision was developed and employed during the Okinawa campaign in the Pacific. Used as a sniper rifle. Took an M1 carbine, put a big infrared illuminator on it and a special sight, and they could use it at night as a sniper rifle. Of course, they had to carry a lead acid battery around with them. So I think this was a 2-man crew. Lead acid batteries are awful heavy. Uh, uh, we also did buried mine detection. They took the treasure finders approach and refined it and quickly built buried mine detectors. They were shipped out first for use in North Africa in 1942 when they invaded, and was used all throughout the war to clear mines. They were built in the thousands or the hundreds at least. It would sweep over, you'd sweep it back and forth until you detected something, and it'd give an audio signal to the operator, who would then go, okay, there is one. I'm going to go hide while you disarm it, or something to that effect. Degaussing of ships. We talked about the magnetic mines. Well, the ships, any ship that's made of steel will create its own magnetic signature by going through the water, basically passing through the Earth's magnetic field. It induces a magnetic field on the hull. So because of that magnetic field, you could build a mine that was looking for magnetic fields. And then when the ship went over, you could explode it. And the Germans used that. So what the British came up with was degaussing the ship, putting a copper wire around the hull of the ship to reverse the polarity and eliminate the field in that was on the ship. And that's what I just said. Oh, okay. I got to figure out how to get. Oh, I can move you. Dennis's picture was in the way. I couldn't see the rest of my slides. IFS transponders. This was an effort to use radar technology to be able to identify friend and foe. If you've got an aircraft incoming, or ship, but normally aircraft, I want to know whether I want to shoot at it or not. Because of the speed, you can't wait until they get close. So they developed IFF transponders using radar technology. One that would send a query to the aircraft, the other, and then a signal would come back and say, "Hey, I'm a friend, don't shoot." So they were used during the war. Do I have dates? I don't think so. No. Almost the last one here. Combat information centers. These were developed primarily by the Navy after some of the big Navy battles that did not go well. A lot of the problems were attributed to the fact that there was poor communication and inability for commanders to know what was going on. So they started to put in combat information centers in ships. Some ships were retrofitted with them, and then all of the newer ships as they were built had them built in. So you had radar stations and communications, and I'm sure you've seen them depicted many times in modern days in movies and TV. But this was a development of the war, and it started retrofitting in 1943. So that by the end of the war, especially when they were starting to get so many kamikaze attacks, they were able to use the combat information centers to more readily react to them. And that was the end. So I feel like I've been on a marathon race. I didn't think I would get through every slide. But so any questions?
So there's also a really good Tom Hanks and Steven Spielberg series on Apple TV about World War II and about a lot of things that John is talking about here. You saw them on the airplanes when they were going into the bombing raids into Germany and all of that. But because this would be way over my head, except I know I watched it with him, so I know.
Yeah, it's called Masters of the Air. It's a very good series, very bloody series, but it was a very good, accurate series.
It was short. It was like 6 or 7.
It was 9 episodes. It was on the 100th bomb group, which had the nickname of the Bloody 100th because of their casualty hit rates.
18
They-
went, 18 would go
Yeah.
out, one would come back.
They came over early in the war with 135 crewmen, and at one point there was one left. So it was really bad. Do you have a question?
Do you know the book, the autobiography of Reginald Jones
I
called The Wizard War? He was the head of British scientific intelligence.
I'll have to look for it.
Yeah, he talks about Freya and G and dealing with the V1s.
I will look for
Really
that.
good book.
I'll add that to my long
The
list of
Wizard
things to
War,
the
Reginald
Wizard War.
I'll remember that.
Yeah, she'll remember it. Any questions from anybody here or out there in the electronic world?
So actually, I kind of appreciate how many inventions were done during the war. Say
A lot.
few hundred.
I would say thousands. If I go back to, let's see, where is it? No. So remember, I talked at the beginning about the Office of Scientific Research and Development. They had over 3,000 patents,
Wow. Okay.
and certainly they didn't have all the patents that were developed. They were just the ones that they were funding. Now this went into all kinds of scientific research, because now it include penicillin and health medical kinds of development as well. But they were a lot. When I started this, I figured I'll probably have 12 or 15 things to talk about. And, you know, I started looking, and this thing would mention something else. Okay, I'll add that. I'll save that website. And I finally got to where I was looking at this. I had a list of websites, about 100 long. And then I got one that says, here's all these different project names. And it goes into, you know, a huge list. There were so many sub-projects and spin-off projects that I couldn't conclude them all. I mean, I'm amazed I got this in the time we'd had. Of course, I talk fast. So again, I'm done. Any questions? Otherwise, I'm going to stand up and let my back dry out. Sitting here in the coat while I'm.
Different generation.
Oh yes. That
Navigating the Pacific with some blips on an O-scope. I could barely find my mailbox without GPS.
Oh, I know. I mean,
Yeah.
well, and you listen to, you read or watch like Masters of the Air, the navigators, you know, he's I won't say guessing, but he's saying, okay, we're heading in this direction. We're flying at this speed. I think the wind speed is this. And I'm looking at the ground for significant locations, but, you know, they're only kind of guessing to get to the general direction. You know, aircraft would get lost all the time. That's the reason why Loran became so important. Is, you know, aircraft would get lost and go down. You know, they just disappeared. It's like that. It's you know, all the time. It was a different time, and flying. You know, we think of flying today as nothing. I mean, we fly all the time, but back then, I mean, you were in a risky environment when you were on an aircraft. They kept breaking. I mean, you know, engines would go out or other things would happen. They weren't just all shot down. They just had mechanical problems. If you run into a storm, you know, what would happen? It could throw you off by hundreds of miles, and then you're out over the Atlantic somewhere, and where do you land? So yes, you're very right there.
Example, the bombing of the Japan cities, drop the bomb and then fly to China, land somewhere in some beach. They both say.
Yeah, that's when in 1942 Doolittle took off with the B-25s. That's what he did. They just had to take off too early, so most of them didn't quite make the landing fields in China. They were 150 miles shy of where they intended to launch. But and I mentioned here, you talk about the different different people. The British determined early on in the war to fly all their bombing missions over Germany at night. They thought it was safer. The Americans, on the other hand, flew daylight missions. The British thought we were crazy. And a lot of aircraft were shot down. But
Was there any cool things from the Axis side?
yes.
I mean, besides the, the beacon.
Well, I mean, they had radio guided bombs. They used them off of Italy when we invaded Italy to blow up a couple of ships. They had radar. It was not as developed as ours, but they had radar. They had their night fighters. They would vector in using radar. Night fighters on the British when they would come in to bomb at night. They had a lot of jamming technology. As I talked before, they had magnetic mines.
So one of the key differences that the Germans didn't have with radar was the planned position indicator.
Or the magnetron.
Or the magnetron. Yeah, what the Germans did was they had a single antenna and they aimed it at a target aircraft, and they tracked that aircraft and then measured by range and position on the antenna where that aircraft was and radioed back to their interceptors. We did not have a PPI. They couldn't see the outline.
That's a big factor. I wasn't aware of that.
Huge factor. Yeah, the PPI was crucial.
Yeah, but yes, the Germans had a lot of developments. The Japanese had some, but not as many. They had radar, or primitive radar as well, but it wasn't as good as the US radar. Can't think of anything else. I think I've talked enough.
They split the atom first, though, didn't they?
I'm sorry?
They split the atom first.
The Germans?
I think so.
Yes, they did. At Heidelberg University, I believe.
Yeah.
And that was done in the 30s. And that was a big fear of the Allies, that the Germans were going to develop the bomb first. So they targeted the development center in Germany, then the Germans distributed it. They went into Norway to destroy the heavy water facility. They missed it. They destroyed the facility, but the shipment had already gone, and resistance ended up sinking a ferry with a lot of civilians on it that was carrying it. But there was the fear. But Hitler was so scatterbrained that he did not focus development on the atom bomb or a lot of things. He was at one point during the war, and it was towards the end of the war, after June of 44, when the best attempt on killing him happened by his own people. Now, he got so paranoid afterwards. Now, the British considered going in with SAS or some special forces and try to assassinate him. And after they assess it, they go, we're better off with him in power because he screws up so much stuff that, like their jet aircraft. I can't think of the. Yeah, with the Messerschmitt and Ju-282 or whatever it is. They had it working. They showed it to Hitler and goes, I want it to be a bomber. And so they had to go back and retrofit and redesign it to make it a fighter bomber. And that delayed it by a year or something. So he just did stuff that he wanted to do.
Open mouth, insert foot.
Exactly. And after the attempt on his life, he didn't trust anybody. The only people he trusted were the SS, and he didn't trust his generals. So it didn't matter what they told him. He did his own thing.
Yeah.
Bill, do you want to stop recording it? Or whoever is doing it?
Yeah, I'm doing it.
Oh, okay. All right. Well, I'm going to stop sharing here.
Thank you, John.
Thank you.
Yeah.
Well, I hope you
Thank you.
enjoyed it. I enjoyed doing it. I enjoyed the research, except I was still working on it about 3 o'clock this afternoon.
It's tense.
Good job, John.
Hello?
Said, good job, John.
Thank you.
So just want to make sure John is in the red and the one displays at Dennis is attending, but he was not speaking. So any question from the other audience? And good night, and thank you, John, and the rest of you. So look out for our announcement for the live member lunch in November. And have a good week. Okay, bye.